All right, welcome back. So I want to sort of make this connection between matrix equations and differential equations very explicit. Okay, so let's say we had a matrix equation or a linear system. This is one from the book: 2x1 plus x3 equals -1, -3 x1 plus x2 plus 4x3 equals 1, and then -x1 plus x2 plus 5x3 equals 0. Okay, I'm going to write this as a matrix system. Okay, so when I write this as a matrix system, I'm going to have 2, 0, 1, -3, 1, 4, -1, 1, 5. Okay, so I'm just taking the coefficients here and putting them in the matrix. And then I'm imagining x1, x2, x3 here. And on the right-hand side, I get -1, 1, 0. Okay, so again, what I'm doing is 2 times x1, 0 times x2, plus x3 gives me that -1. -3x1 plus 1x2 plus 4x3 equals that 1. -1x1 plus 1x2 plus 5x3 equals 0. Okay, so now if I want to think about this in terms of linear systems or the language of linear independence, then what I'm saying is that -1, 1, 0 is a linear combination of the vectors 2, -3, -1, 0, 1, 1, 1, 4, 5. Okay, and we could solve that very easily. Let's go ahead just real quick and do that. Let me go to my not allowed to share the screen. Let me just go to my calculator. So my matrix was 2, 0, 1, -3, 1, 4, -1, 1, 5. Sure, okay. My B vector was -1, 1, 0. I'm going to do it the way that I said. I said, like, I'm going to take the inverse of A times B. And so I get -0.375, which I should be able to reduce that. That's 3/8 and -1/4. Okay. So back to here. So I get x1 is -3/8. x2 is 0, and x3 is negative 1/4. Let me just double check that. What I got. Yep. Okay, so we have this linear combination. Okay, now let's take a look at the same sort of thing with a differential equation. So the differential equation we want to look at is, let's solve y triple prime minus y prime equals 0 with y of 0 equals 2, y prime of 0 equals 3, and y double prime of 0 equals negative 1. Okay, so let's go ahead and solve this system. We're going to make the same assumption that we've been making, that y equals e to the RT. Okay, so y prime is r e to the RT, y double prime is r squared e to the RT, and y triple prime is r cubed e to the RT. Okay, so our differential equation becomes an algebraic equation, r cubed minus r equals 0, factoring out an r, so r equals 0, r equals negative 1, and r equals 1. Okay, so our solution is a linear combination of 1, that's for the r equals 0, right? E to the 0 is 1, e to the negative t, and e to the t. Okay, so our y of t is going to be c0 times, let's say times 1, plus c1 e to the t plus c, well, let's call it negative 1 e to the negative t. Okay, now let's actually call that c2. Okay, and we have to satisfy those initial conditions. Okay, so you can see now sort of this, the point here I was trying to make is I want to make the connection between solving these linear differential equations and solving these problems in linear algebra. Okay, and basically this boils down to the same thing, right? Because now when we do this, we're going to get a system. Y of 0 equals 2, so that means C0 plus C1 plus C2 equals 2. Okay. Y prime of 0 equals 3 is going to give us C1 minus C2 equals 3. Okay, the negative sign comes from taking the derivative here. And then y double prime of 0 equals negative 1 gives us C1 plus C2 equals negative 1. Okay, so we get a system. Okay, incidentally, you can solve this. I solved it earlier to get C0 equals 3, C1 equals 1, and C2 equals negative 2. Okay, so our solution, our general solution is then, let me move this out of the way. Y of t equals 3 plus e to the t minus 2e to the negative t. Okay, but the theory behind how we're going to attack or how we're going to approach this differential equation is intimately related to the theory into how we approach solving this problem. Okay? All right, I'll see you in the next videos.